So we talked about cylinders, and now I want to talk with you a little bit about quadratic surfaces. And these are the graphs, quadratic surfaces are the graphs of equations where the degree of each term is less than or equal to 2. And rather than try and write down exactly what that means, I'm just going to show you via examples. So here is a quadratic equation. So we could have an x squared plus a z squared minus an xy plus y plus z equals 3yz. And so the degree of this term is 2. Degree of this term is 2. That should be clear enough. The degree of this term, well, you add up the number of variables, one variable. So this is degree 2, degree 1, degree 1, degree 2. So everything is less than 2. So this is a quadratic surface. What about this one? X squared plus xyz equals 2xy. This is a degree 3 term, so this is not a quadratic surface, or you could say equation if you want, but if the graph of this would not be a quadratic surface. And so the big moral of the story is when you're graphing cylinders, you just graph the 2D version and then stretch it. When you're graphing other surfaces, and we're going to focus on quadratic surfaces in this section, you want to use what's called traces. And you can think about these as slices. And so what I want to do with you is work through a series of examples. We're going to do it by hand, and we're going to use traces like you would by hand. Then we're going to flip over to Mathematica each time, and I've got everything set up where we can see the graph and the slice and the trace as well. So let's just dive into this together. So our first quadratic surface, this is a classic. This is going to be your friend. We're going to use this, study this graph again and again and again this semester. Z is x squared plus y squared. So this is going to be fun. All right, well, notice that on this side of the equation, everything is always positive. X squared plus y squared can never be negative. The smallest this can be is 0. And so what that means is that z is always greater than or equal to 0. There is no graph down here for negative z because that's never going to fit this equation. Z has to be positive. All right, so traces. Let's begin to do a couple of traces so you can see what's going on. Traces, you just simply fix one of the variables. So when you fix a z, think about it with me, z equals 1. I'm going to slice the graph with the plane z equals 1 and see how it cuts the graph. So if I do the trace for z equals 1, then I get 1 equals x squared plus y squared. I can graph that. That's just the unit circle. That's the trace. This is the trace if you want to. Yeah, you could put it on the xy axis, but I'm just going to graph it. If I do z equals 5, I get 5 is x squared plus y squared. I'll put little arrows here. And I get a bigger circle. And so you can sort of see what's happening. These circles are all centered at the origin. And so let's go ahead and realize what's happening. I get a little circle here. And then I get an even, whoa. That's not quite what we want. Maybe we could move that one over. No. I think that kind of works. Okay. If I go up a little bit, the higher you go, the larger z value, the bigger circle that you get. I'm not sure that this auto graph thing is going to work for us. Here, I'll just do it myself if I can. So the traces look like that. Now let's think about the other traces. So you don't have to slice it horizontal like we did. You could also slice it this way by fixing a certain x variable. That was actually not how we want. There we go. Fix an x, and you get a slice that looks like that. What kind of graph are we going to get? Well, if I fix x, let's say x equals 1, then I get z equals 1 plus y squared, and I can graph that. You should recognize that in 2 dimensions. This is a, let's make this the y-axis and the z-axis. All we've done is just shift the standard quadratic up 1. And so when I slice x equals 1, let's look on the graph now. When I slice x equals 1, I get this parabola opening up like that, and all of a sudden, to me, the graph is pretty clear. Let's do one more trace just so you can see it. You do as many as you need. At this point, I think I've got it, but still, if y is 0, if I fix y equals 0, so that means I'm slicing, whoops, I'm slicing, I need to undo this. Go away. Boy, I'm not sure. There we go. That was a disaster. I want to get rid of that line that I drew. There it is. Okay. So if I'm slicing this along y equals 0, what intersection am I going to get when it cuts the graph? What shape am I going to get when it cuts the graph? So look at your equation. Y equals 0. You get z equals x squared. And this is going to be a quadratic again in x-axis, z-axis. It's just a standard quadratic. And so hopefully at this point you recognize that the actual surface is this sort of almost a cone, but the end is going to be rounded, opening up. Whoops, I missed my circle here. Opening up, looking something like that. And maybe my bottom graph, actually, I should just delete that. It's maybe we'll put one up here. There we go, where you can see it better. Okay, so it's this surface, and the circles help us understand what the 3D surface. The surface is just the outside. It's just the outside of this all the way around the outside, and it's like this bowl. It's infinitely thin, and it's sort of has the shape as pictured here. So I'll shade it in a little bit. All right, so that was a rough hand sketch. Let's go ahead and switch to Mathematica, and we'll actually be able to see a nice graph of the surface and also see these traces as well. All right, so I wanted to show you Mathematica's graph for the paraboloid z equals x squared plus y squared. I'm not sure that I wrote it down in the notes, but that we call this graph a paraboloid. And there it is. You can kind of spin it around and look at it here. Kind of fun. Now, notice that the graph, we've sort of sliced it off at z equals, I think, 5. But the graph actually goes on forever. You just can't see the whole thing at once. Now, I wanted to show you the traces. And so the first trace, we're going to fix y values. You can see that when I fix a y value, I'm looking at this from a little different orientation than we're used to. We usually look at it from this direction. Mathematica defaulted us over here, no problem. I would spin it, but for whatever reason, it's really hard to spin when it's in this double graph here. So I'm fixing y values. These are negative y values, and even though this plane, if you extend it up, it does hit the graph, it won't show up in the little box, the 2D box that I graphed over here. But when you pick small enough y values, then the plane actually, you can see the intersection curve. And that's exactly the intersection curve here. So when you sketch this trace, that's exactly the result of the intersection between the plane y equals whatever and the surface. That when you intersect two surfaces, you get some kind of a curve. And so you can watch how those curves, the curve here, the intersection curve matches perfectly with the trace. So I hope that helps you understand what you're doing when you actually graph traces. You're actually graphing an intersection. And that, of course, helps you make sense of what you find. So here, somewhere in here, I'm looking for it right there. Oop, I had it. Somewhere right in there is y equals 0. And you can see y equals 0, the intersection curve, you get this nice big parabola. And then we keep going, and they go back up and up and up. So that's traces when you're fixing y. Let's fix x now. So now I'm fixing x. Again, my perspective here is a little different than we're used to. X is negative, and all of a sudden you can see that intersection curve showing up in our trace. This is the right-hand side is what you would graph when you were to plug in x equals, let's say, I don't know, -4 or something into your surface. You get a 2D graph. That's what you would graph. This is what's actually happening on the left-hand side, and you can bring it through and you can watch, and we're going to get to x equals 0 somewhere right in there is x equals 0, and then we go positive x's and the graphs begin to go back up and they correspond. All right, one more of these. Let's do the z traces. So we're going to fix a z value. And we said at the beginning that when z is negative, there is no graph. And so you can see there's nothing to intersect with. Bring it up to z value, and all of a sudden, I begin to get an intersection curve. It's very tiny, but I'm looking, yeah, there it is, right? When you fix a z variable, you get circles. So that's maybe z equals, looks like about a little under 1, and z equals 1.5, and so on and so forth. You just keep going up, and when you do that, you intersect and get these circles over here. So let's stop here, and we'll do another example back on the iPad.